Village of Lake George sign, you know, the one you see right as you turn into the area right by the beach.
Tessa has the story from Lake George.
Well, the village of Lake George may be going away.
Lake George, nestled at the southern edge of New York's Adirondack Mountains, is a place more known for summer tourism than seismic risk. But beneath its tranquil surface, something has stirred, and satellites have noticed. In the past week, a European Sentinel-1 satellite picked up a faint yet measurable seismic wave pattern, rippling along a section of the Lake George fault line that has long been considered dormant. This isn't just an isolated blip. It's a minor ground deformation, consistent with low-frequency tectonic movement. While the magnitude of the event was too small to be felt, it wasn't too small to matter. Experts from the USGS and Columbia University's Lamont Doherty Earth Observatory
to take action.
I mean, if we have the power to change climate, we have the power to repair the damage to climate.
Columbia's Earth Institute is the greatest collection of climate scientists in the world.
Are now investigating whether this movement represents stress accumulation or a deeper shift in the region's tectonic behavior. In this video, we'll break down the satellite data, what it might mean for Lake George and the surrounding areas, and whether the East Coast's quiet faults are waking up. The seismic signal from space. The detection began with INSAR, Interferometric Synthetic Aperture Radar, data from Sentinel-1, which revealed subtle horizontal displacement of terrain.
The European Space Agency said Sentinel-1A is launched to a height of 700 kilometers above Earth, where it will orbit around the Earth via the two poles.
Along the western shore of Lake George, the displacement, measured at just over 4 millimeters, coincided with a cluster of low-frequency microquakes recorded on the same day by ground-based seismic stations. These types of slow, unfelt earthquakes, often called aseismic creep, are common in areas where stress builds up silently. But along the Lake George fault line, such activity is exceedingly rare. In fact, this is the first time satellites have ever captured a measurable ground shift in this region. To verify the readings, geologists cross-referenced with GPS stations near Bolton Landing and Hewlett's Landing. The stations registered slight directional shifts, confirming that this wasn't a sensor anomaly. It was real ground movement. The displacement vectors pointed in opposing directions, suggesting a shear-type motion indicative of strike-slip fault behavior, a style of tectonic movement rarely associated with this part of the Northeast. In response to these findings, scientists deployed temporary tilt meters and extensometers along the western shoreline to monitor changes in slope angle and ground extension. These devices are capable of detecting minute variations in earth tilt or surface spreading, offering additional insight into the dynamics of the suspected fault slip. Preliminary data from these instruments showed diurnal fluctuations aligned with tidal loading, an effect sometimes observed in shallow fault systems, pointing to a fault zone that is both sensitive and dynamic. What's especially intriguing is the shape and alignment of the deformation. It appears to follow a northeast-southwest fracture plane, consistent with the mapped Lake George fault line, an ancient structure once linked to Appalachian tectonic processes. That fault has been quiet for thousands of years, until now. Additionally, electromagnetic sensors installed for a separate hydrothermal study inadvertently captured transient electromagnetic EM signals in sync with the seismic microquakes. These EM spikes are hypothesized to be associated with rapid stress redistribution or possible fluid movements through microfractures. While the signals were weak, their timing and correlation with both seismic and INSAR data further strengthen the hypothesis of reawakening fault activity. To contextualize these signals, scientists are developing 3D crustal models using a combination of seismic reflection data, borehole logs from nearby geotechnical studies, and magnetotelluric surveys. These models aim to visualize the geometry and continuity of the fault, determine whether the observed displacement is localized or part of a broader regional strain pattern, and assess whether any fault branches might intersect with critical infrastructure. This confluence of space-based, ground-based, and electromagnetic observations suggests that the Lake George fault line, while still not classified as hazardous, is no longer inert. Instead, it may be entering a new phase of tectonic sensitivity, one that warrants close and continuous observation in the months ahead. What's beneath the fault line? The Lake George fault line is part of a broader network of ancient buried faults extending through the northeastern U.S., many of which have been considered inactive. But recent advances in seismic imaging have shown that even these old systems can experience episodic reactivation, especially when influenced by changes in stress, groundwater levels, or crustal rebound. One theory gaining traction is that crustal unloading due to melting snowpack and seasonal aquifer shifts may be subtly influencing the stress regime beneath the region. These shifts, while minor, can be enough to reactivate deep fractures. This phenomenon has been well documented in glacially rebounding zones of Canada and Scandinavia, where post-glacial uplift has led to renewed seismicity. At Lake George, the topographic relief and historical glaciation suggest that residual tectonic stress may still linger in the lithosphere, waiting for the right trigger. Adding to the complexity, researchers have also begun investigating whether deep-seated fluid migration plays a role in altering fault stability. Using resistivity imaging and borehole fluid sampling, early evidence indicates that pressure gradients between confined aquifers could be introducing transient pore pressure changes at fault interfaces. These subtle increases in pore pressure can lower the effective frictional resistance along fault planes, making it easier for stress to be released in the form of slow slips or microquakes. Additionally, seismologists are reviewing historical earthquake catalogs for overlooked patterns. A 2.2 magnitude quake recorded nearby in 2010, once dismissed as insignificant, is now being reconsidered as part of a larger fault creep sequence. When paired with newly digitized analog seismogram records from the 1970s and 1980s, a subtle cluster of low-magnitude quakes appears to trace the outline of a previously unmapped fault strand running parallel to the known Lake George lineament. This has led to renewed geological fieldwork in the area. LiDAR scans and trenching studies are being conducted along possible surface expressions of the fault, searching for evidence of past displacement events. Preliminary trench results have revealed offset sedimentary layers that could indicate surface rupture during prehistoric earthquakes. If radiocarbon dating confirms these findings, it would establish Lake George's tectonic past as more active than previously thought. Microseismic sensors have been recalibrated in the region, and a temporary array has been installed to capture real-time ground movement over the next few months. Scientists are also testing water chemistry near fault-fed springs, hoping to detect changes in mineral content that could signal fluid movement through deep rock layers. One particularly promising indicator is an increase in dissolved helium-4 concentrations, a noble gas that can be released from fractured basement rocks during tectonic activity. Together, these efforts suggest that the Lake George fault line is more than a relic of geologic history. It may be part of a quiet but active tectonic system. Whether it remains benign or becomes more volatile depends on the complex interaction between hydrology, crustal stress, and time. For now, scientists are watching closely, piecing together a puzzle that could reshape our understanding of seismic hazards in the Northeast. Could this signal a greater risk? While there's no current indication of an imminent quake, the detection of any seismic deformation in a traditionally stable region raises important questions. Could there be more stress building beneath Lake George than previously thought? And what happens if that stress finds release? Geologists warn that while the Adirondacks are not a high-risk seismic zone, they are not immune. Several minor quakes have occurred in the region over the past century, enough to warrant caution. Historical records note quakes of magnitude 3.5 to 4.0 occurring in upstate New York, with reports of mild structural damage and rockfalls in rural areas. In some cases, lake shorelines experienced minor slumping, and well levels fluctuated for days afterward. What elevates concern is the relatively shallow depth of these quakes, typically less than 10 kilometers. Shallow quakes, even if low in magnitude, can result in disproportionately strong surface shaking, especially in sediment-rich valleys like those surrounding Lake George. This poses a notable risk to heritage architecture, many of which are built on older stone foundations, not engineered to withstand horizontal ground motion. Moreover, infrastructure near the lake, bridges, dams, and historical buildings were not constructed with seismic risk in mind. Even a modest quake could cause structural damage if centered near populated areas. The Lake George wastewater treatment plant and electrical substations along Route 9N are now being reviewed for structural vulnerability. To anticipate possible outcomes, engineers are running scenario-based models, simulating events ranging from magnitude 3.0 to 5.5, with varied epicenters. Early results suggest that ground acceleration in some zones could exceed modern code thresholds for utilities and schools, particularly in Queensbury and Fort Anne. Officials are now working with geoscientists to model potential worst-case scenarios and improve readiness protocols. These include drone-based inspection routes, backup water systems, and alternate access points should main roads be compromised. New York State's Division of Homeland Security and Emergency Services has initiated a joint task force with local county responders to pre-stage emergency supplies and map out risk communication networks. At the same time, public awareness campaigns are being launched to educate residents and businesses about what to do in the rare event of seismic activity in the area. Schools are integrating earthquake preparedness into emergency drills. New signage is being considered for hiking trails and lakeside campsites, instructing visitors on what to do if a quake strikes while outdoors. Radio stations across Warren County are participating in a pilot alert system that uses the Emergency Alert System, EAS, for quake notifications, similar to tornado and flood warning. Although a significant earthquake remains unlikely, the goal is resilience, not reaction. In a place long considered geologically quiet, Lake George's recent activity serves as a call to preparedness, rooted in science, safety, and foresight. Tidal forcing and seismic triggers. Recent studies are also exploring the role of tidal forces in modulating seismic behavior along fault zones like Lake George. Although typically associated with ocean tides, gravitational interactions between the Earth, Moon, and Sun can cause minute but regular stress changes in the Earth's crust. These stress oscillations, typically on the order of 0.1 to 0.5 kilopascals, are relatively weak compared to tectonic forces, but can still influence microseismicity, particularly in areas where faults are already critically stressed. At Lake George, tilt meters and strain meters have detected subtle rhythmic stress changes that correspond with lunar cycles. Notably, several microquakes recorded by the temporary seismic array in the region appeared to cluster around periods of peak lunar alignment, when the gravitational pull of the Moon and Sun combine to exert maximum force. This has led researchers to propose that some of the aseismic creep observed may in fact be tidally modulated. Researchers from Columbia University's Lamont Doherty Earth Observatory are using high-resolution spectral analysis to identify correlations between microquake timing and tidal phases. Early results suggest that certain segments of the Lake George Fault respond more strongly during spring tides when the moon is either full or new. This phase-dependent sensitivity is consistent with findings in other intraplate seismic regions, such as the New Madrid seismic zone and parts of central Taiwan. In a parallel effort, geophysicists are modeling how these tidal stresses interact with the geometry of the fault itself. Using finite element analysis, they've simulated stress redistribution across hypothetical fault planes of varying dips and orientations. The models show that even a small periodic stress increase, if applied in resonance with the fault's natural oscillation period, could incrementally weaken locked segments, promoting episodic slip or fault creep. Importantly, these studies are not suggesting that tidal forces alone cause earthquakes. Rather, they act as a triggering mechanism in systems that are already primed for failure. In this context, understanding tidal modulation provides a valuable forecasting tool, indicating when fault zones may be temporarily more susceptible to rupture. Researchers are also examining whether fluid pressures in the fault zone fluctuate in sync with tidal loading. In some volcanic regions, tidal cycles have been shown to drive fluid migration through porous rock, altering pore pressure and contributing to seismicity. While Lake George is not volcanic, the presence of fault-fed springs suggests there may be a hydrologic component worth investigating. To that end, borehole pressure sensors have been installed near key spring outlets to monitor cyclical variations. If these sensors detect phase-locked changes in fluid pressure, it would support the hypothesis that tidal forcing is not just a mechanical driver, but a fluid dynamic one as well. Modeling the effects of these gravitational tides on local fault planes could help researchers predict periods of elevated seismic susceptibility. While we can't control the moon or the tides, understanding their influence gives scientists a new lens through which to interpret seemingly random patterns in fault behavior and possibly anticipate what comes next. Crustal thinning and thermal gradients. Another factor now under investigation is the thermal regime beneath the Adirondack Mountain. Geological data suggests that the crust in parts of upstate New York is thinner than previously believed, particularly along fault-intersected terrains. Thinner crust can be more vulnerable to stress reactivation due to reduced lithostatic pressure. In Lake George's case, elevated geothermal gradients measured through borehole temperature profiling and magnetotelluric conductivity data suggest that heat flow from the mantle may be subtly influencing rheological properties at mid-crustal depths. These thermal anomalies could soften fault zones, reducing their mechanical strength and making them more susceptible to low-magnitude stress redistribution. What makes this particularly compelling is the spatial overlap between zones of crustal thinning and regions of recent seismic microactivity. Researchers using passive seismic tomography have mapped areas of unusually low seismic wave velocities extending from 15 to 30 kilometers beneath the surface. These low-velocity zones are interpreted as partially molten or ductile layers, potentially acting as mechanical weak points in the crust. Additionally, the thermal gradient data show a consistent increase in heat flux in the vicinity of Lake George, with values reaching nearly 70 milliwatts per square meter, significantly above the northeastern U.S. average of 40 to 50 milliwatts per square meter. This excess heat could be driving thermally induced changes in mineral stability and phase transitions, weakening fault interfaces and encouraging fault creep. Petrological modeling suggests that heat-driven metamorphic reactions at mid-crustal depths could be releasing water and CO2 into surrounding rock pores, further decreasing rock strength and increasing the likelihood of slow slip events. These models are being validated through fluid inclusion studies from deep rock cores extracted in nearby boreholes, where elevated concentrations of volatiles have been confirmed. One emerging hypothesis is that localized mantle upwelling beneath the Adirondacks could be supplying both heat and buoyant materials to the lower crust. Magnetotelluric data supports this idea, showing high conductivity anomalies below the Mohawk Valley Fault Zone, which may extend northeastward toward Lake George. If this upwelling is affecting crustal composition and rheology, it could explain why this long dormant fault line is showing renewed activity. To further assess the thermal regime, the USGS is collaborating with academic institutions to deploy new heat flow probes and expand the network of borehole thermometers in the region. These instruments will allow real-time monitoring of subsurface temperature shifts and provide data for calibrating numerical models of heat transport and mechanical stress accumulation. Ultimately, the hope is that this expanded data set will clarify whether elevated heat flow is a driver or a symptom of the fault's awakening. Isostatic rebound and deep-rooted uplift. One of the more long-term processes potentially contributing to the region's tectonic responsiveness is isostatic rebound. Lake George lies within a region that was heavily glaciated during the last ice age. As thick ice sheets melted approximately 12,000 years ago, the underlying crust began to rebound upward, a process that is still ongoing today. GPS data suggests that the area continues to rise at a rate of 1 to 2 millimeters per year. Though this may seem minor, over decades it represents a significant redistribution of crustal stress. Recent modeling suggests that areas undergoing rebound can experience episodic seismic activity even millennia after deglaciation. These models show that the crust behaves viscoelastically, meaning the response is not instantaneous, but continues long after the ice has disappeared. The upper crust, in particular, retains stress accumulated from glacial loading and slowly releases it through aseismic deformation or minor seismic events. Studies from comparable post-glacial regions in Scandinavia and Canada have shown that isostatic rebound, meaning the response is not instantaneous, but continues long after the ice has disappeared. The upper crust, in particular, retains stress accumulated from glacial loading and slowly releases it through aseismic deformation or minor seismic events. Studies from comparable post-glacial regions in Scandinavia and Canada have shown that isostatic rebound can create new fault slip zones or enhance the reactivation of ancient shear zones. In some cases, seismic swarms have been linked directly to rebound-induced stress accumulation. Researchers are now applying these comparative models to the Adirondack region to determine if similar mechanisms could be operating beneath Lake George. Seismologists have also begun deploying horizontal strain meters to monitor the lateral effects of uplift on the regional crust. These instruments help detect whether the vertical motion is accompanied by horizontal stretching, an indicator that the lithosphere is adjusting not just vertically, but in all dimensions. Preliminary data shows weak but measurable extensional strain across the region. Complementing these mechanical models, isotopic analysis of carbonate deposits along ancient lake terraces has revealed subtle changes in elevation consistent with tectonic tilting over the past 10,000 years. These terraces act as natural markers, recording the landscape's response to rebound over geologic timescales. By aligning these terraces with GPS and LiDAR data, scientists can track the rate and pattern of crustal uplift and deformation with unprecedented precision. One significant concern is that rebound-driven stress changes may not occur gradually and uniformly. Instead, they may produce stress gradients that concentrate along existing fault lines. This could explain why the Lake George fault line, once considered dormant, is showing signs of renewed motion, Even small additions of stress in a fault zone already near failure could tip the balance, leading to slow slip events or clusters of microquakes. Going forward, researchers aim to integrate rebound dynamics into regional hazard assessments and 3D geodynamic simulations. These enhanced models will account not only for plate tectonic motion, but also for surface mass redistribution from melting glaciers, snowpack variations, and hydrologic shifts. The goal is to better understand how the legacy of ancient ice continues to shape the seismic character of Lake George today, and how that influence may evolve in a warming world where ice mass is once again in flux. Listening to the quiet Earth. Lake George may appear still, but deep below, the Earth has sent a subtle message, a reminder that no place is truly geologically silent. The satellite detection of this minor seismic wave is a wake-up call, not of panic, but of preparedness, because even small signals matter when it comes to the planet's shifting crust. Is this a one-off occurrence, or the first whisper of a long, quiet fault line stirring to life? Let us know your thoughts in the comments. Share this video with someone who lives near the Adirondacks, and don't forget to subscribe and hit the bell icon for future updates, because the Earth is always speaking. The question is, are we listening?